Hola guys, welcome back to another lecture. So today we'll be looking at a new topic in the same topic of anti-infectives, that is urinary tract anti-infectives. A urinary tract infection is any infection that affects any part of the urinary tract. Now the urinary tract is made up of four parts, that is the kidney, ureter, bladder and urethra. So four parts: kidney, ureter, bladder, urethra. Now UTI are mostly caused by bacteria. Okay. Now UTIs are most common in women as compared to men. This is because women will have a shorter um, urinary tract, whereas men will have a long urinary tract. So if urinary tract infections occur in women, they will usually be less complicated as compared to that of men, because men have a longer urinary tract. Now, urinary tract we said was made up of four parts: kidney, ureter, bladder, urethra. Now, kidney and ureter, these two make up the upper urinary tract, and whereas the bladder and the urethra will make up the lower urinary tract. Next we have urinary tract infections. We will classify them on the basis of whether they are in the lower urinary tract or in the upper urinary tract. If they are in the lower urinary tract, we will call them lower UTI, bladder infection or cystitis. Now since we said the lower urinary tract consists of the bladder and the urethra, so we will call it a lower urinary tract infection or a bladder infection or just simple cystitis. Now if there is an upper urinary tract infection, we can call it a kidney infection or a pyelonephritis. Kidney infection because the kidney and the ureters are affected, so kidney infection or pyelonephritis. Next we have the signs and symptoms. So the signs and symptoms includes burning micturition, abdominal pain, urge for urination and blood in the urine. There will be also flank pain. Next we have urinary tract anti-infectives. So what are urinary tract anti-infectives? Urinary tract anti-infectives are the agents which help to treat and prevent urinary tract infections. Now, what should be the ideal properties of any urinary tract anti-infective? They should be easy to administer, they should have minimal side effects, and they should be inexpensive. They also should be able to attain urine concentrations and tissue concentration. Now urine concentration if the lumen of the urinary tract is affected, and tissue concentrations if the kidney is affected. That is, it should exceed the MIC, that is the minimum inhibitory concentration for uropathogen, by at least 4 folds. Next we have the classification of urinary tract anti-infectives. In that we have two major classifications. One is quinolones and the second one is miscellaneous. So in quinolones we will have many quinolones like enoxacin, ciprofloxacin, moxifloxacin. In miscellaneous we will have furazolidone, nitrofurantoin and methenamine. Now let us talk about the chemistry of quinolones. Now as we know, quinolone antibiotics is a member of a large group of broad spectrum bactericidals, okay, that share a bicyclic core structure which is related to the substance 4-quinolone. Now as you can see 4-quinolone right here. 4-quinolone is like a naphthalene ring with a double bond O and a nitrogen in the ring. So this is 4-quinolone. Now for a quinolone, what we will have is we will have the double bond O, and the nitrogen which will be attached to R group. Along with that we will have something extra like a COOH group, X group right here, 7th position some R group, and 6th position some R group. So this will be extra. So the majority of quinolones in the clinical use belong to the second generation, that is mostly the class of fluoroquinolones. Fluoroquinolones, they have a true quinoline framework. They also maintain the C3 carboxylic acid group and add a fluorine atom to the carbon containing ring, typically at the C6 or the C7 position. That is, the fluorine group can be either here or here on the basis of the structure. Then next is, they are effective against both gram-negative as well as gram-positive bacteria. Now let us look at the mechanism of action of quinolones. So mechanism of action of quinolones are that they have a basic quinolone nucleus, as we said, 4-quinolone. it inhibits DNA gyrase and topoisomerase 4. So please remember DNA gyrase and topoisomerase 4. Here 4 is very important because there are other topoisomerase enzymes as well. So topoisomerase 4, and thereby it prevents the unwinding of the DNA, that is the double stranded DNA to a single stranded DNA, and it will inhibit replication and DNA synthesis, which will lead to ultimately the death of the bacteria. Now when it comes to gram-negative organisms, DNA gyrase helps in the death of the bacteria, whereas in gram-positive we have topoisomerase 4, which plays a major role in the death of the bacteria. Now in the classification of quinolones, the quinolones are classified into 4 generations according to the American Academy of Family Physicians. So we have generation like first generation, second generation, third generation and fourth generation. Now these are based on spectrum of activity of these quinolones. Now for example, the first generation of quinolones, what will happen is the examples of first generation quinolones are nalidixic acid, synoxacin, norfloxacin, lomifloxacin. Now, nalidixic acid and synoxacin, they have a gram-negative action, or they have a activity against gram-negative bacteria, excluding the Pseudomonas species. Whereas norfloxacin and lomifloxacin, they have a gram-negative bacteria which includes the Pseudomonas species. In the second generation, we see enoxacin, ofloxacin, ciprofloxacin, levofloxacin, sparfloxacin. Initial members like enoxacin, ofloxacin, these have a gram negative activity as well as a slight gram positive activity. Whereas when we come for the later drugs of the second generation, that is ciprofloxacin, levofloxacin, sparfloxacin, this will have a gram positive as well as a gram negative activity. Here there was gram negative along with a mild gram positive activity. Now next we have the third generation. In the third generation we have gatifloxacin and moxifloxacin. So in in this third generation we will have, they have gram positive activity, gram negative activity, plus they also have activity against atypical organisms. Whereas in the fourth generation we have trovafloxacin. So trovafloxacin has action against gram positive, gram negative, atypical and additionally it also has action against anaerobes. So this was the classification of quinolones. Now let us look at the structures of quinolones. We will start with the first generation, that is nalidixic acid. Now let us look at the general structure. What is it? We have to draw two benzene rings which are fused to each other. Now since it is based on the structure of 4-quinolone, we will give it that same structure. We will give it a double bond O and a nitrogen in the ring. Then we said there was a COOH here, and then we will have a nitrogen here as well, and then here there was a R group, so here we will give a CH3 and here we will give a C2H5. So this is the structure of nalidixic acid. So what did we do? We drew two benzene rings fused to each other, each having, so we will first draw the basic structure of a quinolone, that is a double bond O and a nitrogen in the first ring. Then to make it a quinolone, we will add COOH here, and then to this nitrogen we add a C2H5, and to this carbon right here, that is the 7th position, we give a CH3. Next we have enoxacin. For the structure of enoxacin, we will draw the same basic structure, that is two benzene rings which are fused together, a double bond O and a nitrogen in the ring, give the double bonds. Next we give the COOH, then we give the nitrogen right here. We have to give one here and one here. Now in oxygen, the only difference between, and then here we will give a C2H5. In here, what is the difference between enoxacin and nalidixic acid is, here there would be a piperazine ring. That is a 6-membered ring with 2 nitrogens on the opposite sides. And here in the C6 position, we will give a fluorine group. So this is your structure of enoxacin. Now in norfloxacin, it's the same as enoxacin, the only difference being from enoxacin to norfloxacin is the removal of N in this position. So the structure of norfloxacin will go something like 2 benzene rings which are fused to each other. We'll give the basic double bond O here, the nitrogen in the ring here, the COOH here, double bonds, the C2H5 here, then the fluorine here, the piperazine here. But the only thing we will not put is the nitrogen right here. So this will be your norfloxacin. So remember, it will be nor. It will be a nor. Nor means there is no nitrogen. Next we have ciprofloxacin. Now ciprofloxacin will be the basic structure for all our upcoming drugs. So in ciprofloxacin we will draw the same thing. We'll start from the basics, that is 2 benzene rings fused to each other, a double bond O, a nitrogen, the double bonds in the ring, then we will give a COOH, then a fluorine right here, and here we will give a piperazine. No nitrogens in this ring from now on. And then to this nitrogen, instead of giving a straight like 2 carbons, we will give a 3 carbon ring. So a cyclic 3 carbon compound, that is cyclopropane would be added to this nitrogen. So this will give you ciprofloxacin. Now let us move on to lomifloxacin. In lomifloxacin, what we will do is we will add the same basic ring first. We'll draw the 4-quinolone first. Double bond O, a nitrogen right here, the double bonds in the rings, then we give the COOH, then here we will give the fluorine group, then the piperazine right here, and then hydrogen here to make up the valency. The same with the hydrogen right here to make up the valency. Then next we will add CH3 group right here, and here we will add a fluorine group. To this nitrogen again we will give a CH2 CH3. So this is our lomifloxacin. Next we have gatifloxacin. So gatifloxacin is the same as ciprofloxacin, just the only change would be this group right here and this group right here. So gatifloxacin, first we'll draw ciprofloxacin, that is 2 benzene rings attached to each other, then a double bond O, a nitrogen, so our 4-quinolone is ready. Next we add COOH, and then we will add a cyclopropane right here, a piperazine right here, then a fluorine group right here, and to this ring we will add a CH3 group right here and a methoxy group right here. So this will give us our gatifloxacin. Next we have sparfloxacin. In sparfloxacin, we will draw the same structure as that of lomifloxacin. So like lomi, we will have, first we'll draw the basic structure, that is 2 benzene rings fused to each other, a double bond O, a nitrogen right here, the double bonds. Then right here we'll give a COOH, a fluorine group attached here, a piperazine ring attached here. This time instead of just one we will give two. So CH3, CH3 and a fluorine group right here, like lomifloxacin. Cyclopropane group. So this is your sparfloxacin. Next we have levofloxacin. Now this levofloxacin structure which I have given here is a little twisted, so we'll draw it again. So we'll start with the basics, that is two benzene rings fused to each other. We'll make a 4-quinolone first, so double bond O, a nitrogen in the ring, a double bond right here and double bonds in this ring. Then we will give a COOH here. In this ring we will have a fluorine group attached here, a piperazine attached right here. Now what we do here is, attached to this nitrogen instead of the hydrogen we will give a CH3 group, and then here we'll take a carbon from here, give it an oxygen and complete it as a benzene ring. So this will give you your, along with the CH3 right here. So this will give you your levofloxacin. Next we have moxifloxacin. So how do we draw moxifloxacin? Moxifloxacin would be the same basic ring. We make it a 4-quinolone. Then we give it a COOH. Then we give it a fluorine. Now here, instead of a 6-member ring, we give it a 5-member ring. After this 5-member ring, we give it a 6-member ring with a nitrogen at the tip. To make up the valency, we give it a hydrogen. Then right here, we give it a OCH3 group, and then here we give it a cyclopropane. So this will give you your moxifloxacin. In the miscellaneous groups, we have 3 drugs actually: nitrofurazolidine, nitrofurantoin and methenamine. Now furazolidine we already started in the local infectives chapter. So now we will go on to nitrofurantoin. In nitrofurantoin, so nitro, furan and toin. So this means a nitro group, a furan group and a toin means a hydrogen toin group. So this is our hydrogen toin group. So we give a nitro group first. We'll draw a nitro, attach this nitro to a furan ring and then hydrogen toin. So we'll attach CH double bond N connected to another N, which is connected to C double bond O, NH, CH2, C double bond O, another NH. So this will give you a nitrofurantoin. Next we have methenamine. So in methenamine, it's a very easy structure. First we draw a benzene, then we draw a W under it. We attach this tip to this tip here. So we'll attach it like this. Then we give nitrogen at alternating positions. So nitrogen here, a nitrogen right here, and a nitrogen right here. So this will give you your methenamine. So for the synthesis of methenamine, we will take the starting material of formaldehyde. So H, C double bond O, H, a formaldehyde, and we will add ammonia to it. So NH3, 4 molecules of ammonia, and we will do cyclization. Through cyclization, we will get methenamine, that is a 6-membered benzene ring, a W like this one attached to this one right here, and then nitrogens at alternating positions. Nitrogen here, and a nitrogen here, along with 6 molecules of water. So we have the synthesis of nitrofurantoin. Now the structure of nitrofurantoin is something like this: a furan ring. Attached to this is a nitro group. Then we have a CH with a double bond N connected to another N, which is in a 5-membered ring. Next to the N is a double bond O, then another NH, another double bond O. Now this is a nitrofurantoin. So the starting product, we will take this part. But instead of CH2 or CH3 here, we will take a 5-nitrofurfural. So this is an aldehyde group right here. Now if this is the 5th position, we have 5-nitro, since it's a furan ring, for fural because it is a aldehyde group. Next we will add to it 1 amino identoin. So 1 amine group added to a identoin group. So 1 amino identoin. So we have, in the presence of NaOH, there would be removal of water. So there is a H2 removal from here and an oxygen removal from here. So we will get a double bond between both of these. So CH attached to a double bond, N, which is attached to a N, and then the full ring. For the synthesis of ciprofloxacin, first we'll draw the structure of ciprofloxacin. The structure of ciprofloxacin is something like this: 2 benzene rings fused to each other. Then we have a COOH group here, a double bond O here, a nitrogen here, the double bonds in the rings, a fluorine here, a piperazine ring here, and a cyclopropane attached right here. For the starting material, we will try to take a ring which looks something like this one. So we will take a benzene ring with a benzoyl chloride. Attached to this, we have in the 2nd and 4th position, we will have chlorine groups. In the 5th position, we have a fluorine group. Now to this we will add dimethyl malonate. So dimethyl malonate will look like CH2, C double bond O, O, C2H5. Same thing here, C double bond O, O, C2H5. Now we will remove HCl from this Cl and this H. So this will be attached directly to this one. So we get, let us see in the structure here, C double bond O, attached to it a carbon, this carbon. Then attached to it we will have this group and this group. So attached to this CO2 ET, that is C2H5. Here also C double bond O, C2H5. Now from this, by addition of water, we will do 2 steps. First step and second step. First step would be removal of C2H5OH, that is C2H5 and the OH from the water. Then we already have CO2 here, so we will remove this CO2 as well. So this full group will be eliminated. So we will get C double bond O, this C attached to nothing else. Here we will have C double bond O, O, ET. Then we will have, in the presence of triethoxymethane. Now this group right here, if you see, there are 3 ethoxy groups. So triethoxymethane, we will have removal of C2H5OH. Now if there is removal of C2H5OH, what will happen is this part. There will be addition of another C and then OET. So this group will be attached right here with a double bond. We will replace this OET with cyclopropylamine. So cyclopropylamine in the presence of ethanol. So there will be removal of another C2H5OH, that is this group right here will be removed. C2H5O and a H from here. So instead of that H, we will attach this NH2 right here. So NH2 with a cyclopropyl. So cyclopropylamide will be attached over here. To this we will add K2CO3 in the presence of DMF. So when we add K2CO3 in the presence of DMF, we will get removal of HCl. So which HCl will be removed here? A hydrogen from here and a Cl from here, and there will be cyclization. So because of cyclization, this HCl will be removed. Nitrogen will come right here with the cyclopropyl group here. Next we have there would be a concentrated H2SO4 added to this. So this ethyl group will be converted to OH group or hydrogen group. So we will have C double bond OH here. Next is we will add a piperazine group here to replace this chlorine. So there will be removal of HCl, this H and this Cl. So it will attach right here and it will give us a ciprofloxacin. Thank you. That was all we had for today. I hope you all understood the lecture and I hope I made it as easy as possible. If you have any suggestions for us to improve our content, please let me know in the comments below. And I hope you all find these classes interesting. So until next time, thank you. Mogasu.